Robotics, degree obtained with honors at the Scuola Superior Sant'Anna of Advanced Studies, Pisa, on November 20, 2012. Also holds a professional qualification as an engineer in Section A of the industrial sector granted by the University of Pisa on February 29, 2008. He holds a master's degree in automation engineering in December 2006 and a bachelor's degree in computer engineering in May 2003, both degrees obtained at the University of Pisa. For the research areas, its main areas of interest include systems theory and process control, real-time and digital control systems, guidance in navigation systems, mechatronics and microcontrollers, robotics and haptics, field robotics, physical simulation and 2D and 3D virtual environments, virtual reality, machine learning, artificial intelligence, and intelligent systems. For the professional experience, since January 2013, Dr. Tripicchio has served as Executive Director and Scientific Program Manager at the Gustavo Stefani Advanced Robotics Research Center in La Spezia. Moreover, since August 1st, 2019, he is Assistant Professor RTDA at Scuola Superior Sant'Anna, funded by the DSIP Institute with the Department of Excellence in Robotics and Artificial Intelligence. For the projects and publication, he has participated in more than 13 European Union projects, including Monitor 2021, Luxottica 2019, Continental ESV 11, Trenodrome, 3D Virtual Baby Hearth, and Testa Mouse, among others. He has more than 100 articles published in prestigious journals with more than 1,500 citations of this work. The mechanics for this magistral conference will be the next one. Doctor, you'll have 1 hour and 15 minutes for your opponents. And Doctor, if you allow me, I will announce you when you have 10 minutes left. And at the end of this presentation, we will have allocated time for questions and answers. And now I give the floor to Paolo Tripicchio. Dr. Paolo Tripicchio, sorry.
Okay, thank you. I will try to share my screen. Okay. You can see, right? Yes. Okay, so I go. Okay, and this talk I will present applications of robotics and artificial intelligence in the context of industrial applications. Okay? Thank you for your introduction. Basically, I prepared here a slide from my background. I'm a senior researcher in the Scuola Superiore Sant'Anna, and my application areas are reported here in these 3 big balloons. So I work on the interconnection between robotics, human-computer interaction, and artificial intelligence. Okay, I participated to several industrial and European projects, but I have a really good background with the industrial partners that are world leaders in their specific area. So for this reason, I decided to talk to you about industrial applications. As we all know, humans have experienced different industrial revolutions during the years, starting from the first revolution that depicts the improvement from manual handicrafts to the use of tools, mechanical tools in principle, to create some products. And so it is characterized by mechanics and the use of steam or water power, so hydraulics. Okay. Then we have Industry 2.0, so the second industrial revolution, that instead sees the introduction of electrical power and the first creation of mass production, so assembly lines inside the industry. With the third revolution, we have electronics that takes the advent. So we have computers and robots. So if we think about robots, the first prototypes for industry are of the 50s. Okay. And today we are in what we know as is called like Industry 4.0 or 5.0. Basically, there are a lot of techniques or of disciplines that are fused together, and we are trying to focus on the human, so on human-centric in industry. In particular, the Industry 4.0 has been founded worldwide at the European or US or even in Italian program, focusing on many pillar technologies, like the one that are shown here. So, for instance, additive manufacturing for 3D printing of parts, or augmented reality, or Internet of Things, industrial internet, and introducing also the artificial intelligence through big data analytics and applications. So what I want to discuss today is what we have to expect, from the industrial point of view, where we are moving, and to try to solve the demands, the difficulties that could arise in the next industrial scenarios. We have to ask ourselves what are the demands that the market and these scenarios search for. So the first consideration is that for sure we are moving from environments that are completely structured, so we know every phase, every single line, what should do, and instead we are moving to unstructured ones. So we don't know a priori the sequence of action that we have to perform to accomplish a given task. The second aspect is that many processes in industry today requires the flexibility of the humans. The flexibility from a point of view of cognition and perception, so to understand what has to be done and to perceive the environment and the aspects, the complication that could be in the environment, and of course also adapt. If we look at manipulation capability, so adapt the way we interact with objects and tools within the industry. A third aspect is that we are moving back from what was mass production to instead realizing customized products. So for each client could go on the internet and order a specific product, but customized for his needs. So we need to be able to reconfigure the cell to adjust the process to create a specific products. Okay. So the paradigm is shifting from what the simple by design paradigm, or with the Latin motto divide et impera. So I decompose a complex problem in several small parts so that I can manage easily to solve these parts. Instead, we are going back and we have to face the uncertainty. So this is something that in field robotics is done every day. So basically, we have to construct a model that represents the world, that takes into account uncertainty. So the fact that I cannot easily model everything, so there is some sorts of noise in the process, and I have to deal with that. So how can we do this? Basically, we have three elements that are common elements for every control engineer. The first element is the sensing. Okay, so the idea is that I can create or put new sensor into the process. So sensors that allow me to measure something that I couldn't measure before, or I can, for instance, is an application that I've done a few years ago, where we 3D printed robotic fingers, okay, with the aim of creating these conduits to place in the conduits fiber optics. This fiber optics is used to sense the stress and the strain of interaction with objects, okay? So in this case, the principle is really simple. We use Bragg effect. So basically, this is the fiber core, and we write on the core these gratings. Basically, we make these parts of the core opaque, and when the light is injected into the fiber, so you see the injected light, part of the light is reflected back, okay, on the reader, depending on certain wavelengths that depends on how I wrote the grating on the core. So basically, what happens if I apply a force, so I deform this core, this wavelength changes, so I can measure measuring the change of wavelength, I can measure the deformation. I can measure, in this case, the force of contact, okay? This, for instance, allows us to see if an object that I've grasped is sliding down, and so I need to adjust the force for making the object not fall from the grasp, okay? But when we are talking about sensing, we don't refer only to the use of new sensor or integration of sense, but also how we process the information, okay? So in this case, there is the field of artificial intelligence. We know that we can build some particular architecture that allows us to be more robust, to improve our measurements. In this case of the video, in this video, we have an actor that we developed where we transform a classical pose detection that is instance level. That means that has been trained on specific instances of objects to a category level. This means that now, even if I never trained this network showing a specific bottle, for instance, he is capable of recognize the concept of bottle in general, so to estimate the pose of the object that he never saw during training. So the second element is the actuation. Again, here we can integrate new concepts, new materials, new way of actuate, for instance, again in the grippers, and perform actions into the world. Here is an example of an electroadhesive gripper that we developed. Basically, we replaced the fingers of the robot with this pad, electroadhesive pad, and as you see, we are able both to grasp object and also to sense, looking at the capacitance of the circuit, if the object is fallen from the grasp, okay? So in this case, we have integrated both actuation and sensing together. The third element is the control. So in this case, again, we can insert intelligent controllers. So we can build artificial intelligence algorithm directly inside the controller. For instance, here we have an application of imitation learning. So we can train our control strategies directly in simulation, in this case using a couple of graph neural network in cascade. The system is able to understand the sequence of motion and task that it has to accomplish, starting from one single image, in this case, one single image of the goal configuration that I want to achieve, okay? And then I can train on simulation and transfer this directly to real world to verify if our approach, our algorithm is robust enough to work on real scenarios. So I will start now to show you some applications specific to, in this case, to the field of robotic manipulation. That is one of the, say, the biggest application area in industry. So when we talk about robotic manipulation, the main problem that we have to do is the problem of picking and placing objects, okay, in an environment. So we have three elements in this problem. One is our robot. Another is the vision system, so the sensing system we discussed before, and then we have the object to be picked or raised. So the first action, if we want to, let's say, the simplest approach to solve this problem is the one called detect first, then grasp. So we have a first phase that is detection. So our vision system should try to identify an object from a certain description, a certain mathematical model of the object itself. Once I have detected this object, I can give a command to the robot to go and grasp this object. So this example, we have some key points that are exactly the three elements that I presented before. So the first element is we have to design a gripper. So we have a part of actuation that should be designed. Then we have the development of the vision algorithm, so it's the sensing. And third is the control that is needed to plan the sequence of movement and action that the robot has to do to achieve the grasping of the object. These problems have different level of difficulties. We start from single object. This is the most simple. So we have a single object on an empty space. Then we can have multiple objects. So we can have interaction between objects. And then we can have the problem of clutter in the environment. So we have a lot of objects that can occlude themselves. Okay, so we have a clutter of objects. And to analyze this problem, Amazon started what's called Amazon Picking Challenge in 2015 and 2017, trying to stress the research on this topic and proposing some challenges that should be done and a set of objects to be picked by robots. A solution that have been presented in literature present, for instance, different approach from the classic one. They reverse the approach for to reduce the timing needed to accomplish this problem. And so their approach was grasp first, then recognize. So they grasp an object, then they see, okay, is the correct object or is another one, okay? And to win the competition, they adopted multiple strategies, multiple gripping solutions. In this sense, they have 2 fingers for parallel gripping, and here this element in red is a suction cup, so that can be retracted or advanced. So basically, they developed 2 artificial intelligence algorithms. The first, called multi-force and grasping network, that decides which grasping primitives to use. They define these grasping primitives, the suction down, so from the top down, suction from the side, or grasping down, or flush grasp is if the object is really close to the border of the beam. Okay, and training a network that highlights the highest value for each of the grasping primitives. Instead, for recognizing the object after it has been grasped, they use another approach, still in artificial intelligence, called cross-domain image matching, where they used a Siamese network to verify where the object that they see from the real images lies on the feature space, and if it's close to one of the objects they trained during simulation, they can match and say, okay, this object is the object that I already know. Okay. Other approach, more classical, are the common approach used in two-finger grippers that needs as sensing element a 3D sensor. In this case, a sensor that could be a RGBD camera or also a laser scanner that they should provide a point cloud. A point cloud, so we have not only information about the color, but also about the 3D shape of the objects. This is needed because there is the need to verify the normals to the objects and find two opposing normals to use this parallel grasp. So when for every surface that possess these capabilities, I can generate a grasp hypothesis and then select the best one to use. So another approach instead can be used employing a different actuator. In this case, this is a gripper called universal jamming gripper that is made by a plastic membrane filled with granular material like coffee grains, and use a suction to remove air from this membrane. Okay, what is obtained is that this membrane apply to the object that we want to grasp three different kind of forces. So we have a static friction with the object, we can have interlocking, and of course we have also the suction activities. Okay. The idea was to test both the classic approach with the two-finger gripper, and then we developed a custom universal jamming gripper, and we create a system using ROS to control the whole architecture. So we started testing this system using this set of objects that we selected. And these sets of objects was selected because they have different properties. And in particular, we were interested in checking the problem of reflective materials, so that could affect the vision system, or the porosity of the material, in this case of the carton box, that change of porosity can change the way the object adheres to the gripper itself, or objects that can deform, or that have not symmetric center of gravity, and so on. And with varying weights, of course, all the weights should be give the possibility to the robot to lift up the object. So since we have used a robot that was not so performant, the weight wouldn't be too much large. So this is a sequence of our algorithm that we implemented. Basically, we used this is a depth map taken from a Kinect camera, and in each image of the sequence, you see that there are some highlighted elements. In this case, an edge of the cap. Here is instead the corner of this Vivident gum pack, and so on. So we define an algorithm that was able to detect edges and corners, because we wanted to use this feature as input for the picking using the universal jamming gripper. And this is a sequence where you see in the first sequence there are all the objects. After the cap was removed by the robot, the cap is no more here. So the depth map changed a little bit because it's scaled with the color and so on. until I arrive to objects. For instance, here, the closest object to the robot was this carton box, but it's too big to be picked, so the robot selects instead another element that is lower, the lower 8. So here is the system at work. So you see the real scenario and the let's say the virtual representation of the system in Gazebo. And here you see the real-time output of the vision system. Okay, so we can decide to pick some object with the jamming gripper or with the classical gripper in this case. Okay. And what we achieved is that our system was really competitive with the existing system. So the one I showed you before, so the MIT Princeton solution, and then the classic antipoda grasp. But the real interesting point is that the timing, that using our simple computer vision algorithm, we could scale down the time really much. So not only we achieved a good success rate, but also we reduced timing. Okay. Now, instead, I want to talk to you about a problem that is related to the flexibility of the human. This is an application that we have done because this kind of task in the industry is usually performed by human personnel. Why? Because these objects that we have to manipulate, that are Ray-Ban glasses, okay, are really deformable, okay? And the problem is that these glasses have to be attached to this is a frame for the galvanic bath. But both the hooks on the frame can be deformed, and also the nostril part are really deformable. So humans can easily adjust these parts during the attaching phase, but instead with robots it is much more complicated. So we had to use computer vision and control to achieve this result. So in particular, we had to identify the position of all the hooks in the frame, the position of the glasses on the conveyor belt, the position of the bridge between inside the glass frame, the position of the hooks and of these nose pads in real time. And we have done this using support vector machine classifier. That is one of the most used machine learning approach. Okay. What we obtain here is that this is the phase of picking. So the robot approaches the glass, then it localizes the bridge in the center of the glass, and then is able to go and pick this glass. This phase allows to be able to pick different versions, different models of the glass, okay? Because we adjust to the glass itself. And we are not restricted on how to grasp this glass. The second part is the hooking. So we have to approach the frame, then recognize the position of the hooks and of the deformed nose pod, and adjust doing this kind of pivotal rotation, adjust the elements to attach the glass to the frame. You see here, there is a video. This is at low speed because it was one of the first experiments. So we used a linear guide to open the hooks, then the glasses are put close. There is computer vision that analyze and measure the position of the hooks and pads in real time, and then we compute a sequence of motion that allows to attach the glass to the frame, and as you see, this is attached. And here we have a video in, let's say, the normal speed that they show you how all the operation is done. And we achieved this system with the speed time of 7, a cycle time of 7 seconds was the goal to be obtained. So we were able to, using computer vision, artificial intelligence, we were able to adapt the system so to be flexible and so to replace a task that is usually performed by human personnel. Another important element to analyze is the planning. Okay, we have to be able to pick and place an object. There is the need to verify if we are able to perform a certain motion in space, and in particular, taking into account possible collision. So we have to analyze mathematically and determine a set of motion of the robot that avoids collision. And in particular, what we are interested is the task that we have to accomplish. So basically, you see here, we can have an end-over. So basically, I pick an object, in this case is a screwdriver, to pass the object to a human. So that is an end-over. And so in this case, I will prefer to pick the screwdriver from the top parts, not from the handle, because I have to pass the handle to the user. Instead, if I have to use a tool to use, in this case, it's better if I pick it from the handle because I have to use. So we have to define constraints that should be optimized in the problem that we want to solve to be able to correctly pick and use or place an object in the space. And working on these topics, we discovered that the existing benchmark to verify the capability of the system were limited. So we decided to propose a new benchmark trying to solve the limitation of the previous one. One of the limitations is that usually existing benchmark select fixed location for object to be picked, but the idea is that if you have an industrial problem, of course, you cannot decide beforehand where an object should be. No, so we decide to remove this constraint. Moreover, the classical benchmark does not consider clutter. So instead, we were really interested in clutter machines like this one. So we have been picking with full of object, and we decided not to be limited to a single aspect of the pipeline. So we tried to analyze in our benchmark both vision, planning, control, and grasp. And so we identify an idea that allowed us to generate a score, so evaluate with a score the clutter, and so that a scenario, even if it's different from another one, I can compare the two scenarios and the result that I have with my system on this scenario. This benchmark has been selected, and at the last ICRA 2024, that is the main conference on robotic automation, was picked as one of the official challenge. So to realize this benchmark, we start, of course, from existing benchmark. We didn't want to to reinvent from scratch everything. So we selected some object from the YCB benchmark, from the Amazon Picking Challenge I introduced before, and from TLS, this is another benchmark. And some of the objects instead we had to change because they were not more available, or you cannot buy them currently. So we select only object that is possible to buy, and to buy them worldwide, so not only on one region of the world. Okay. Then we try to select objects that propose different materials and properties, actually for stressing the system that we want to test. And so we performed an evaluation questionnaire and given to the research community to evaluate the difficulty of picking every single object. Okay. And thanks to this evaluation, we were able to generate these 4 subsets. So there are 4 subsets of 10 objects, and so the benchmark can be run on the first subset, second, the third, or the fourth, or on the full set of 40 objects together. These subsets have increasing the difficulty. So the subset 1 is the simplest one, and the subset 4 is more difficult. In fact, you see there is, for instance, the glass that is transparent, so it's difficult to see the glass with the camera, or there is a t-shirt or globe that is deformable, so it's difficult to pick a deformable object, and so on. And we defined a protocol that is divided in stages. So basically, the first stage regards tasks that are simple. So we have just a problem of vision of individual object, or pick and place of individual object, or pick and place of object in cluttered. Okay. The second stage instead is intended for training artificial intelligence or computer vision techniques, because we have pick and place of individual object or object in clutter, but unknown. So object that I didn't use during training. So I don't know which object it is, but I try to pick the object nevertheless. And then there is the third stage where, of course, we have the most complex one, because I want to pick object in a cluttered environment, but in a given sequence. So I have a sequence that specifies, okay, the first object that I want to grasp is a toy duck, the second is a book, the third is a t-shirt. Okay, so instead, in all the other trials, all the object was non-sequential, so I could just grab the first object, and it was good enough. And to help in doing this, we also realized a dataset. The dataset, so it can be used to test as testing for the benchmark, can be used for training vision and grasping algorithms, and in particular, the dataset having all the objects of the benchmark simulates rigid, soft, and deformable object. For instance, here you see the globe that falls over top of the cheese-it box and deformates on the surface. And we also simulate liquid in simplified manner, so that we can have the Coca-Cola bottle with liquid inside. And the idea of this data is that we realize different versions of the same scenario with different lighting condition and intensity, color, or HDR maps. So these are used to generalize vision algorithms. This is an example of the generation of a subset. So objects are made to fall from a specific point over the bin, and they fall one over the other. And when all the objects of the subset, in this case are 10 objects, are at rest position, we take these images that are used as a data set. Okay, and we pass to the next scenario. So as introduced before, And here is the proof. Basically, we have these 4 subsets, and the difficulty of this scenario is increasing from the first to the fourth. And we define the metrics to compute the difficulty of the scenario that are using the benchmark that depends specifically on this curve that show basically if one object is occluded, so the percentage of occlusion of objects, because objects that are occluded are more difficult to recognize from the vision, but also to pick with a gripper, okay? And to test the benchmark, we realized an architecture that is suitable for multimodal grippers like this one. So this gripper have the ability to grasp with 2 fingers in close position, 2 fingers enlarged with the suction cap on the tip, or it has also magnetic grasping capabilities, can grasp 2 objects at once, and so on. So we define a pipeline that to recognize the object and select grasping position for each object. Here you see a selected position to grasp the banana object with a 2-finger gripping. So it shows you the outline of the fingers. And here instead the same object, so the banana, but the position for the suction cap. Okay, so in this case, it wants to pick the banana from the center. So yes, there are some videos of trials. So we started with the simplest scenario of clutter, that is the what is called structural clutter. So where objects are separated from one from the other. This is instead a dense clutter where objects are one on top of the other, so there is occlusion. And the most difficult is the bin picking, because we have also the constraint of the bin. And here you will see that sometimes it fails, so it tries again, tries to select other objects and so on until is able to perform a pick. In this case, has changed the object and so on. Okay. And the result is basically that starting from a scenario, in this case, we have 3 trials. Since in each trials we shuffle the bin, the object inside the bin have different position and placement. So the idea is that I can compare the result on each trial, because I have this procedure where I segment the object in the bin, and then I compute the occlusion between objects, and based on this occlusion, I can calculate a maximum score, and depending on how much object I was able to grasp, I obtain a score that is normalized with the maximum score that of the scenario. Okay. So for robotics manipulation, this is a short summary. So basically, we have said that we need to model in uncertainty and work in a structured workspace. And to do this, we need to improve the sensing capabilities, so or with AI or with new sensor that can give us more information, or we need to develop and design novel mechanism and principle, or exploit novel material. So, for instance, the use of different gripper, the jamming gripper, and so on. In general, there is the need to embed intelligent behavior, both in hardware and software, and we try to focus on working in cluster, so with different objects and conditions, to provide flexibility, like in the case of the Ray-Ban glasses. And so we realize also a benchmark to analyze the performance of the proposed system. Now, I want to talk about other fields of application industry. One is the logistics. So in this case, the logistics using RFID tags, so radio frequency identification tags, that are used for some scenarios. In particular, they are used for item identification, substituting the classical barcodes, okay, that you find in every product. Then can be used for self-checkout. And but we focus more on the real-time inventory. So the ability to change and update the inventory of a warehouse of a retail store on the fly without the need to go close to each object and rescan the barcode. Okay, so the concept was this one. So I have a robot, mobile robot. I put an antenna, one or more antennas on the robot, and then the robot moves on the floor of this environment and creates a real-time inventory of the objects in the scenario. So to do this, we studied the problem of phase signal. So we have here is a depiction of the reader circuit board where I have transmitter, receiver electronics, an antenna, and this is the tag that has another antenna. We are talking about passive tags. So basically, this tag have no power and is powered by, as I say, by the signal, the electromagnetic signal that arrives on the antenna. So this signal have a phase of the signal because it's a wave that propagates on a medium, and this phase, as is written on this formula, is related to the distance r between the two antennas, and in particular 2 times r, because 2 pi or 2r, 2 times r because the signal have a distance r to move from the interrogating the reader, so the interrogating antenna to the tag, and the same distance to return back to the reader. Okay, so 2 times r. So basically, the idea here was to use what is called a synthetic aperture method. So basically, I move the robot in the environment, so I create basically multiple measurements that so I'm increasing the aperture of my localization techniques. So this is the equation of the measure phase. As you see here, there is a phi 0 that is a value that depends on the electronics of the circuits. But if I do a difference of consecutive readings, so I can remove the phi 0, okay, because this is fixed. So I do a difference, this is removed. So I have an equation delta phi that depends only on the distance r. So the idea is that if I repeat this procedure, so I have multiple measurement on different location because I moved the antenna, I will be able, through trilateration techniques, to measure where a tag is in the space. So one of our works use synthetic aperture, phase unwrapping. This is because the phase is a periodic value, so it changes with the period 2 pi. So we need to unwrap this value to make it continuous and not to go from 0 to 2 pi. And then what happens? This is a scenario where I have a first reading at position AP0 and the second at AP1. So what you see is that this hyperbole, this one in black, is the locus of possible position of the tag because intersect all the circumference centered on the 2 positions. So basically, if I have 2 readings like this, I can know that the tag, the time reading belongs to this hyperbole, but I don't know where. So the idea is that I can perform a motion with the robot, so move on another point and find another hyperbole and intersect the hyperbole and so on. The problem is, of course, that there is uncertainty. There is noise in the measurement. There is noise given by the scenario, the environment. There could be electrical noise or occlusion or other refraction noise and so on. So we propose a quality estimation approach that uses this formula here, that is used to select the best intersection that could estimate the real location of the tags. So, and we obtain, let's say, good resolution because localization error of like 2 centimeters, okay? Then we continue this research, and since we are using synthetic aperture, it's important to understand that we have a problem with the third dimension because our synthetic aperture, since we use a ground robot, is only on the plane XY. Okay, so the robot moves over this plane. So the idea was to move the antenna also in the zeta axis. Okay, and we have done this by creating a rotating motion, so we can achieve this kind of helicoidal motion of the antenna. This is the custom robot we developed with the rotating antennas. As you see, when he's moving in the environment, he's able to produce this trajectory, helicoidal trajectory on the scenario. So we have a synthetic aperture in all the 3 directions, and this improves, in turn, improves our estimation of the localization. I want to show you another a third application that is regards the welding defect detection, so the quality inspection of elements. So basically, the problem was to detect the defects in welding of diesel injector of cars, and basically, so we have to acquire the image of these injectors that are here with an acquisition system. And our commitment asked us to recognize the 4 types of defects. So blow-hole defects, excess or lack of material, misalignment of the center, or the thin or large welding joint. So these 2, the 3 and the 4 defects can be measured by taking an image and fitting circles and measuring elements, okay? But these other 2 elements instead are difficult to measure, are difficult to model. So we decided to use 2 different approaches. For the measurable one, we use classic computer vision, while for the top 2, so the 1, 3, 2, we use a machine learning technique, so a deep neural network that can estimate if there is a blowhole or excess loss of material. So we developed a system with the camera and the illuminator. We designed the illuminator, and then this pipeline that had the 2 steps: computer vision class and deep neural net. So you see here an example of computer vision where we fit circles and some points over the image to measure some quantities. And instead, for the deep neural network, we create a problem that is called binary classification. So we were just interested to understand if the image could be classified as good piece or a scrap piece, or a piece that could be thrown away. But the main problem was that we had few samples. This is a problem common to industry because basically, if there is a good industry, they will produce really few samples of scattered pieces, you know. And the other problem is, again, given to this, the problem of the few samples is the data imbalance. So we had a lot of data of good pieces, but few images of scrap ones. But so we decided to use these architectures called DenseNet. The idea here is that basically this architecture use concatenation on successive layer, and this allows to reduce the dimension of the whole network, so to make the network thinner and compact. So we choose this DenseNet. So to solve the problem of scarcity of example, we decide to apply a technique that's called transfer learning. So basically, we trained our architecture not on images, directly on images of injector heads, but using this public available dataset. It's called material in context dataset. So this dataset has example of different objects with different materials, for instance, brick, carpet, ceramic, fabric. But the idea to use this dataset was because inside this dataset there is the material metal. So since welding is mainly made on metals, we assume that features that are present on this category, that is metal, will allow us to recognize elements and effects on welding. So what we have done, we have done this pre-training with this MINC, so this dataset. And what we can show is that even using just 3 classes, not the full class I presented before, it was enough to obtain a good starting base for the training. Here you see the result, basically, where there is the image acquired, and the first image is the computer vision stage, and the second is the deep neural network. So it can pass the measurement on the image, but it could fail because, for instance, here there is a lack of materials and so on. And in particular, we obtain a result that we could run the inference even in CPU without using GPU, because it's this second, so 0.2, 0.3 second to analyze the images, or in embedded hardware like the Jetson TX. Okay. Then we had another problem. The year after we finished this approach, our customer changed the material with use for the welding. So, and what happens that looking at the images, they have this strange shiny gold, violet nuances. No, so there is something strange. So the architecture we proposed at the beginning didn't work anymore because it was confused between these nuances and the actual defects. Okay. So the idea was to, instead of retraining from scratch, to use a filtering technique. So this is the original image where we cut the central part because it's not used. And we use 2 filters, so patch filter and median filter, to, let's say, in some way normalize the image. And the result was quite good. So basically, we show that using filtering, we could maintain the old architecture. And of course, there was also the problem of data imbalance we said before. So basically, we have different quantity of values for good scrap pieces. And in particular, the problem is more complex if the classes are not easily separable. Here is an example. No, basically, if you want to identify these buttons, this element from this is really simple to understand. This is a different shape, So in the feature space, we have a different cluster. But the other 2 examples, scrap 1, scrap 2, are really close to good. So it's difficult to understand. In this case, this circle is not really perfect. And here there is a dark spot on the board. Okay, so just to give you an example, so we have to understand if the data, if the elements I want to find are close or not. So let's say I want to distinguish between a cat and a dog is simple. I want to distinguish between these kind of elements is more difficult. So to treat data imbalance, there are 2 procedures in literature. Basically, if I have more is the class for system good images, I can reduce the good image to make it balanced, but in this case, I will lose information. The second approach, instead, I take the minority class and I repeat this class to increase the number and achieve the one of the majority class. but in case I can run into overfitting that could be not good choice. So what we have done, we tried a different pre-training and transfer learning, but basically we inserted a weighting in the confusion matrix. So we weighted differently elements of good and scraps values so that we could achieve a good result. As you see here, we were able to obtain 100% in precision and specificity. So basically here, the lesson we learn is that if we have few samples to train, we can use transfer learning. If we have a problem with where there are classes that are evenly unbalanced, we can give different weights to element in confusion matrix or use specific loss functions. And if something change in a certain process, instead of recreating from scratch a new architecture, it's possible to use filtering to realign with the previous architecture. So I conclude showing you just a last example of application. In this case, we talk about digital twin. So a digital replica of some industrial process, in this case, is used for predictive maintenance. So we built a portal equipped with laser and cameras, and when the train passes inside the portal, we are able to scan the train both from the texture and the geometry, and also part of the train like the pantograph. So it is the part that goes in contact with the electric power lines. And then looking at historical data, so previous acquisition of the same train, we can understand if something has changed, if we need to perform maintenance. For instance, we can measure the height of this part that is in contact with the power line. So if it's too thin, we have to change the structure. So we can perform predictive maintenance. So I've given you some example of application, particular here for predictive maintenance, computer vision and artificial intelligence for quality inspection, application of robotics in logistics, and in particular, I talked about robotic manipulation for picking and placing objects, and trying to show you some aspects that are surely important for the industry of the future, where we have to stress our attention. So integrating intelligence inside our hardware and software, and finding new materials, new concepts, new design for actuators, or introducing new sensing elements to solve this problem of the passage from a structured, completely structured environment to an unstructured one. So thank you very much. I concluded here.
Thank you very much, Paolo. We're going to start with the questions. So,
okay,
you have questions?
Hi, doctor. Can you hear me?
Yes, yes.
Okay. I just have two short questions. The first one is, I don't know if you mentioned it, but what kind of code language do you use in your algorithms about AI visual system? And the second one is, what softwares you use in your visual system and robotics simulations?
Okay, so basically, in all our works, we mainly use C++ and Python, okay? For what regards, of course, the artificial intelligence and computer vision application, we use mainly Python, because there is a large community of also of packets or frameworks that you can use. In particular, for learning and quality detection, we use the PyTorch. That is a standard library for you to use tools for, let's say, machine learning and supervised learning. And instead for in robotics, all the community works under the use of ROS. ROS is stands for Robotic Operating System, so it's a framework that gives many tools to perform application like planning, path plan, navigation, control, and gives also simulators like Gazebo. Gazebo is a physical simulator and visualization tools. So if you have instead specific needs, you can go and find, let's say, and give and realize custom implementation, for instance, for graphics with using OpenGL and so on. But the standard is to use ROS and Gazebo for simulation, and Python for sure for all it regards artificial intelligence applications.
Okay. Thank you so much.
You're welcome.
Hi, doctor. This is the beginning for Industry 5.0. But my question is, what is the truth that these robots replace human labor in the future?
Okay. Of course, there will be specific tasks that will be performed only by robots in the future, because they affect the health of the humans. For instance, the specific application I show you of the Ray-Ban glasses, it's really unhealthy for a human worker, because they have to move all the glasses, attach every day. It's a repetitive task, and also cause pain to the back of the human. So for sure, all the task that involves heavily the body of the human person will be replaced in the future. And I think this is a good way to use robotics and artificial intelligence. For sure, this will not mean that human will lose their job. Human will supervise or will do something different, but for sure, a heavy task is better if a machine performs this heavy task. No? I don't know if I answered correctly to your question.
Yes, doctor. Thank you.
Okay, thank you.
Hey, doctor. In talking about clustering objects, you talk about using a Kinect for creating the deep map of the objects. My question is, what is the advantage of using a RGBD camera like a Kinect about using a stereo system or a LiDAR system for computer vision?
Okay, this is a difficult question in the sense that depends on your application, because of course these sensors have different resolution, for instance, have different reliability to different environments. For instance, if I'm outdoor, I have some problems. If I'm indoor, and depends on the lighting of the environment itself. So there is no solution that I can say this camera or this laser is better than the other solution. All depends on the specific application. For sure, laser have a greater cost and have in general higher precision, but depends on your application. Also, the use of stereo system, stereo camera or RGBD again depends on what you want to achieve. For instance, in the case of the Ray-Ban glasses, we had to go really close, let's say, to inspect. These are, let's say, these are the glasses. Okay, I have to inspect these nose pads that are here, but the robot grip the glasses really close. So we have a really small distance from the nose pad to the gripper. This really close distance doesn't allow to use any kind of camera. For instance, at the time we have done the project, there were no RGBD camera that could measure precisely the position of the nosepad at this short distance. So we had to create a stereo pair and compute and create the algorithm by ourselves to analyze these elements that were really close. So it all depends on the application. So also the choice of the optics. For instance, you mentioned the Kinect. The Kinect is is a camera that is not really a professional camera. No? It had we used that because it was low price and easy to use. But if you have particular specifications, you cannot use the Kinect that has let's say high aperture optics, but you have to decide to design your optics that you want to use to put in focus specific elements. So you have to do a study depending on the application and the environment where you want to use your sense.
Thank you.
Right.
Hello, doctor. Can you hear me?
Yes.
Okay. I have one question about this. If we keep studying about this, programming some robots with artificial intelligence, in one future maybe it's going to be to the instrument be optimized. But in the future, so many engineers will lose their job because the robots will make their homeworks. What actions that the engineers we can do when the time will come about that?
Okay. Basically, I think there will be a shift also in the education system. I don't know, with the advent of these artificial intelligence tools, for instance, ChatGPT and so on. All education system, university, but also lower school, are trying to understand how to shift the learning paradigm, because usually at engineering you study the basics, starting from mathematics and physics, how to solve problems, how to write complex algorithms. And then instead, now you have tools that you can go online and tell, oh, my problem is this one. Can you give me the solution? And it will write down the solution. Okay, so which is the compromise? It's better to stick with the old way, so we have to study from scratch, from the basics, or it's better just to say, okay, I just want to be a user of an AI system that gives me the solution. So for sure, the basic are needed. I think it will not be removed because without a proper knowledge, we cannot assess what an artificial intelligence system, for instance, can, if its answer is correct or not. And for this reason, it's not that the old engineer will be replaced. No, it's not replaced. it will act differently. So it will find another way of its job. For sure, if an engineer now is not using artificial intelligence, it will produce less than another guy that is using artificial intelligence. So we have to move to a new way of how we do our jobs. This is my point of view.
Okay, thank you.
Good morning, doctor. I have a question about the application of the artificial vision and the robot arm. For example, in the presentation, I see the position, the home position, but in case of turn off the energy in the space of the arm robot in the middle to peak and in the middle in a peak to an object and turn up the energy, the arm drop the in case of return the energy. What is the movement of the arm if the energy turn off in the middle of the peak of the object and return the energy, the arm drop the object or continue with his picking and position to the object? Sorry for my English.
Okay, so you asked if I lose power. You say with
Yes.
energy.
Yes.
Okay, so if there is no more power, the robot stops, and if the object drops, okay, okay, for sure. All this depends on the robot. If a robot is an industrial robot, so is a robot that it was designed for industry, for sure there is a safety procedure, okay? So if power goes down, I lose power, the condition will be safe. That means I think that in this case, the robot is not backdrivable. It means that you can, if the robot is switched off, you cannot go there and move by your hand. You will not be able because there are brakes, and also because the motion of the joints, the more is done in such a way that it requires a huge amount of torque and force to move a robot. So they are the exact term is they are not backdrivable. Instead, if you have other kind of robots that are not industrial, that maybe you can have in research facilities in the university or haptic interface, for sure, this kind of robot you can move by your hand. And so if the power goes down, everything falls, it's a problem. But in this case, of course, if the power goes down, there will be in industrial setting, there will be an alarm, so everything is safe and the robot stops. Of course, if you want to recover from this, I think right now there are not automatic procedure that you just recover the power and starts from where it was. It recovers the power and starts reboot the system and starts from the beginning. So at least this motion is lost. You have to discard the piece and restart again. I don't know if I answered, if I interpreted correctly your question.
Yes. Thank you.
Okay.
I understand. Thank you, doctor.
Okay.
Hi, doctor. My question is, how does the AI algorithm or the hardware of the robot could be improved to pick up deformable objects?
Okay, so yes, the deformable object. The problem with the deformable object lies in, let's say, the force and the way you approach the grasp. So in general, all solution tries to solve this problem, not really with an algorithm, so not really with the intelligence, but with the hardware. So the design of a specific gripper that maybe is soft, so the actuation is soft. There are a lot of grippers that use what is called variable impedance actuations, so they can adjust the impedance based on the object. So this allows not to the need to model and write mathematical algorithms to account for any possible problem with the formal object, but just you say just okay, close the gripper, and the gripper adapts to the object independently if it's soft or not. So the solution that is most common is this one. But of course, if one want to research, implement some specific algorithm, okay. Yeah, but it's of course cannot be general. It's difficult to generalize on it.
Okay, thank you.
Right.
Hi, doctor. Good morning. Well, some of the first pages of your, some of the first pages of your presentation appears a page where talk about the vision algorithm. So in this page, we saw several images or grayscale images. So I would like to know if you can explain a little bit more about the vision algorithm.
Yes. Okay. Maybe I can share this talk. Okay. Okay, I think you were referring to this one.
Yes.
Okay, so basically, here, as I said, we use the Kinect, no? So the Kinect have an RGB image and a depth image. So this grayscale image is basically a representation of the depth, okay? The idea here is that we wanted to pick objects top down, okay? So pick the first object to pick is the one that is higher from the table, okay? Is in top of the other. So this is easily selected because having at disposal a depth information, that is this image, where the image is darker, it means that we have a higher 8 from the table, okay? So at this point, we have here points that are all the same 8. So we had to decide a strategy on which element we should focus for the picking. Okay, as I show you at the beginning of the presentation, if we use a two-finger gripper, of course, I need to find two opposing faces, because when I close the finger gripper, they have to stretch these opposing faces. In this case, what is shown is the solution for the jamming gripper. So the idea is that in the jamming gripper, you have this membrane, plastic membrane that deforms when you go in contact with the object. And the gripping force depends, maybe, I don't know, okay, so, sorry. Okay. And the gripping force here depends also on the surface of contact with the object, okay? So the idea, so that you can exploit both friction, interlocking, or suction, okay? So the idea was that if we find in the image an edge okay, or a corner. In this case, this is a cap, okay? So if I select a point that is an edge, when I go with my gripper, the membrane will cover both sides of the border of the cap, okay, in this case. Or if I want to pick another object, if I select a corner, instead of just two faces, I will have in this case three faces, no? The top faces and two board, because it's a corner, okay? Like in the case here, no? The mented and the box here have the top face, then this face and the other face that's vertical, okay? So when my gripper goes in this point, I have three surfaces on which I can adhere the gripper. So the idea was that if I search for corners, and if I cannot get a corner, in this case, edges, I have enough surface for my gripper to create a certain force for the grip, okay? So this is the strategy. So basically, the algorithm first search for, okay, select the top object. In this case is easy because you have the depth information, okay? Then it search for a corner. If in this case there is this object have no corner, I search for an edge and I select this point. In the second, when I remove the cap, so sequence 2, the cap is no more here. The object that is higher is this Vivident gum pack, okay? So here, because the geometry of this pack, I can find a corner, and so I select the corner. When I remove this, I find the Mentadent box. Here again, I can find the corner, and I select this. When I remove this, it remains only this card, I don't know how it's called, but to put the cards, okay? And here, basically, there is a kind of keychain, key ring here that is on top. And so on this element, the algorithm finds just an edge, not a corner, and so on. I don't know if now it's more clear, the algorithm.
Yeah, thank
I
you.
hope. Oh, okay.
Okay. The last question is going to be more philosophical question. Until
Okay,
now,
so I skip.
No. Until now, you have shown us or present us the integration of robotics and artificial intelligence in different research that you have done for different industries or different researches that can be applied in the near future. But what's happening in 20 years? Maybe how you can imagine the world of this integration between humans, between robots and artificial intelligence in 20 years?
Okay, I think it's possible, but okay. There is also one part that I didn't show that regards virtual reality. Okay, virtual reality and augmented reality. And there are major players also in this, no? Meta and so on. So there are players that have a huge amount of money and they can push towards certain direction. And of course, you can see also already on the streets people with wearing these head-mounted display, you know, these helmets, and that they are a little bit detached from reality. Okay, but I think that probably, if there is a correct push on that direction, it's possible that most of the industries in the future will be controlled remotely with a virtual environment representation. So I have this virtual environment, I can select the action to do, and remotely robots will do this job and produce everything. So this is one possible scenario. So removing humans from inside the factories and using just virtual replica, digital twins, virtual reality to manage and control all the activities of the factory without going there, without the problem of possible damage of that of the human. But there were periods also in the history where for instance, artificial intelligence was pushed also with games, but they didn't succeed. So we have to see if in the future generation are more, let's say, prone to use virtual entities, virtual device without physical contact. This could be one possible future. Okay, this is just an opinion. It's not.
Yeah. Thank you very much, Paolo. We appreciate your presentation. And just to finish, we are going to read a little letter. Just you want to read it or okay? Okay. Just wait. Okay. So it's a recognition from the Tecnológico Nacional de México that gives you a recognize to Dr. Paolo Tripicchio for your participation in the conference Robotics and Artificial Intelligence for the Industry in the Future. This conference was within the Congreso Internacional de Investigación e Innovación Multidisciplinaria, CIM 2024, from the Orizaba Institute of Technology. Thank you very much, Paolo. We appreciate your time and your knowledge. We are happy with your conference. Thank you very much.
Thank you for your invitation. We are welcome. So I wish you a good continuation of this day and the next day. And I leave. Okay.
Thank you very much.
Bye. Thank
Bye-bye.
you. Thank you. Bye.
Ciao.